Okay, so in this video I am gonna go over the hardware and software integration for the AXI4-Lite interface for the convolutional 2D kernel. So what is this block? If you look into the notes of your Unit 5, right here, I think at one point in the next pages you will see this block. Feel free to look at it. I mean, I think if you go in the website, you will find more information about this, or even on the VHDL slides. But with regards to this particular interface, it's not really relevant what it does. What it matters is how the I/O works. And the way it works, it is simple. We have to fit data here, exactly 72 bits, and once enable is asserted, right, the block starts the computation, and after a while, I think it's about 6 cycles, the output appears on F. It's 20 bits, and the output is going to be signaled by V, by the valid output. So that's all we need to do, okay? And I have already explained, how this interface works, right, in a different video. So let's get to it. So again, what are the steps? The first thing we have to notice is the following: that I have already all the files that we need to integrate this hardware into an embedded system. I think the block is located. You can download, of course, the files from the website, from the tutorial website, okay? So this is it. Let's give me a moment here. Okay, so here you see a bunch of different files. What really matters are the following. So this is the top file for the AXI4-Lite interface. Okay, this is the next file in line. This is a file that contains the slave registers, right, and extra circuitry. And then underneath that's where your design goes, your circuitry goes. And by the circuitry, I mean the following. And this is only, by the way, my suggestion. In this block, at least what I do is to include what we call the glue logic between my circuit, I mean my pure hardware circuit, and the slave register. So what is that? What is this glue logic? So let's go here. Just a moment. Okay. So here you have the interface, okay? And the interface includes, of course, your block itself, the circuit itself, and of course the registers and some extra circuitry. So let me explain to you what we're doing here. So if you were to do the following, see, here. So this block right here, this portion that you see, that would be the this file, my COM2IP, because it includes both the glue logic and that's this state machine and this extra register and this connection here, right, from the slave registers to the input and from the output of this register to the slave register 3, for example. So that's COM2 IP. The kernel itself, that's my block, my design. I think I call it my COM2. I think it's just my COM2, the pure kernel. The block itself, right? My pure hardware. This block right here. Okay. So if you go to the here, this is the following. After this, underneath this we have my COM2 VHD. This is my circuit design. So every circuit that you have, that's the top file. And of course, underneath there are all the files that this top file needs. Okay, so this is the file structure. So this is my suggested design flow. Of course, the first step is to create your circuit itself, right? Which in this case, I'm going to call it my COM2 VHD, for example. So it can be any circuit, by the way. The second step is to add the glue logic, right? Well, I guess let's do it this way. Let's say add the interface circuit, right? And that includes, of course, the glue logic to the slave register signals and the slave register circuitry itself, right? So this glue logic, of course, in this particular case has been implemented in my COM2 IP.phd. And what about the slave register circuitry? That is made up by the COM2 v10.phd and by my COM2 v1.00. So this file, though, as if you remember from a previous example, you need to edit, right? If you remember that, because you need to edit because you need to insert what this block, right, into it. Okay, so that's what I suggest. I mean, you first, of course, create your circuit and then you add the interface circuit. Okay. Again, this is a strong suggestion or a strong recommendation. Create a hardware-only Vivado project for the AXI4-Lite interface. What do I mean by that? Well, remember that since you are creating this glue logic and you are editing this file, there is always a possibility that you are making a mistake, right? It is possible, completely possible. Because of that, you need to complete this very important step. Simulate your AXI4-Lite interface. Okay, so let me show you very quickly what I am talking about. Just a moment. For example, for this circuit, my COM2 with the AXI interface, I have created a pure Vivado project. And this Vivado project includes here a test bench, believe it or not. So here I have a test bench, for example, for this particular example. Okay, and with the test bench, of course, I can actually emulate the AXI interface signals and then check out if or verify if my signals are working the way I intended them to work. Okay, so now the question is, well, somebody can say, well, this I can do. This I can do too. But where am I supposed to get these two files? Well, this is very important, right? Where do I get the silent stems? There are many ways. I mean, just use the ones for a previous project, right? From a previous project, right? And edit, right? Edit the name, for example. That's one way to do it. Another way to do it is to create a sort of quote-unquote dummy or fake Vivado project, and do the create IP so that you can retrieve the silence template with the right names, for example, right? That's what I mean. There are many ways to do it. That's how you would do it. Okay. So once you do that, now you are on step number 3, which is the step that we did for the pixel processor, right? Which is, you remember the previous example, the previous video, which is what? Now properly create the AXI peripheral. I think more than create, let's call it build the AXI peripheral in Vivado, which means create your IP, right? That's how Vivado calls it. And then, of course, integrate the AXI peripheral with software and test. Those are, I think, my recommended steps. Okay. What I've seen in many cases is the following, and it's not uncommon, by the way. Many, let's say, students or first-time designers, they design their interface while they build the AXI peripheral. If you remember, that's sort of what we did for the pixel processor. But in that case, I mean, the pixel processor example was so simple, right? Was so simple that I guess we were very confident that it was gonna work, right? Remember here, the only connections were here and here, so that was so easy. But now in our example, right, that we have, oh, not this one, sorry. Just a moment. It's supposed to be the last one. In this example, of course, it is a bit more complex. So what I did, of course, again, I first created my circuit itself, and of course I simulated that too, and then I created the entire interface and simulated that too. After that, the whole process becomes very mechanical. Okay, so we don't even have to worry about that. Okay, so please keep that in mind next time you want to implement your own hardware. Again, this designing the interface while building the peripheral, it might work, but I would say from experience, not recommended. Okay, because like I said, it is possible that you make mistakes, even however small they are. Okay, so now I have already, of course, completed the first two ones. Okay, and now all that I'm gonna do is to build the peripheral in Vivado. Okay, and that's supposed to be a really easy thing to do. Let's see. So all I have to do is to follow the steps as laid out in the tutorial, which are, by the way, very similar to the previous example, right? The pixel processor. Let's see. Okay, so let's do that, right? I'm sure this step will be pretty straightforward. So we are going to create a new project Give it a little bit of time. There we go. Again, always ensure that it is VHDL, the target language, and then the board, you need to select the Nexus, sorry, the ZYBO, or ZYBO 10, whichever is the one that you're using. In this case, I'm going to select the ZYBO 10, and then I'm done. Okay. So again, what do we do first? We need to build the peripheral in Vivado, okay? So is that I already have the peripheral, all the files that I need, but I have to still build it and package it in Vivado, so it is ready to use in Vivado. Let's give it a little bit of time. Okay, so now what do? We create a new package IP. That's building your peripheral in Vivado. So you can just drag it and drop it. Okay. How should I call it? Again, this step is very important because the name that your files have, it has to match to the peripheral you want to create. If it doesn't match, it will create different template files, and then you have to adjust everything, manually. So here, you do my com2, and there you go. And light slave. How many slave registers? Well, let's take a look. 1, 2, 3, 4, right? Slave registers. Okay. This one here, even though it is a register, it is not a slave register. It is part of the glue logic in your circuit. Okay. So remember, while your job is actually to creating this file, the one in red, because everything else is actually a template, which you might need to make some small additions, of course, minor additions to it. Okay, here we go. And then, of course, we click on here to be able to edit this IP. And a new Vivado project will actually open. Just give it a little time. Okay, let me see. Here is the new Vivado project. And it will show you, of course, it will provide you with the template files. That's the first thing that it's going to do. So those are the two files. Remember, again, let me make a small suggestion here. Remember what I said here about creating a dummy project to just get the silence templates. This could be, if you, want to have the, if you want to, oops. Sorry, just a moment. If you want to be able to retrieve these two files, so you can, simulate the whole AXI4-Lite interface in a different Vivado project, well, yeah, this is where you get it, okay? But of course, I had already done that before, okay? And, well, let me see. Here is the file, like I said. I explained this, by the way, last time. This particular file, the top file, we don't really need to do anything unless you plan to add some extra ports, which you might need at one point, okay, for your project. Other than that, you don't change it. This second file is the one that you need to change, because you are only using three registers, right? And this file assumes that you are using 4 registers for reading and writing. So, and of course, you have to insert your this block, okay? So you have here two options. One option is to, let me see if I can open this file. One option is to just copy and paste the file that you have. This is the file that I have already. Look how slightly different it is, because let me show you just a moment here. For writing, I have a slave register 0, 1, and 2. And look at this. I only uncomment this portion and this portion, the one that corresponds to register 3, and this portion. And then for reading, what did I do? I commented out what? The stuff corresponding to slave register 0, 1, and 2. Okay, and that's all. That's all regarding to using the particular registers, but you also need to insert your block, right? Remember this block? My COM2IP. This is where I make the connection between the slave register signals and my COM2IP. Essentially, it's just connecting the slave register outputs and this input here from the slave register. And I think we also need this signal, a slave register write enable. And that is what is happening right here. Okay? And of course, if you're going to use this block, you have to, let me see if it's, you have to put it in the component, right? And that is all that you need to do. Okay? So what I'm going to do now, I'm going to do what I think I always prefer to do. Instead of editing this file right away, because I could edit this right now to make it look like we only need a certain set of registers for reading or writing. Instead of doing that, I am going to overwrite these two files with the files that I already have. Okay? Which I think, to me, is the best method. I mean, when you develop this kind of interfaces. Okay? Like I said, in the previous example, we did this for the pixel processor, right? Where we edited the file right away on the go. That is not usually recommended, but it's not. It was not a bad idea for the pixel processor because it was very simple. Here, this is more complex, so yeah, we will just copy. So, what should I do then? Well, I need to go to the folder. I'm gonna just close just in case. I need to go to the folder, which is the repository, of course, still, and then my COM2, and I think it's HDL, these two here, and I am gonna copy the file right from my from my zip file, right, where I downloaded, and I'm gonna paste it and overwrite them. There you go. And now if you were to open this, you will see that this is the updated file, right? And there you go. That's it. Okay. Of course, what is the next step? You still need to add the all the blocks, underneath this COM2IP. You need to add the file, manually to this project. So there are many ways to do that. Let me see. The way I do it is I just copy everything, of course, except the test bench, except these two, and even the C file that I need for later. All of that I'm gonna copy them here. Okay. And what do I do now? I'm gonna add sources. I'm gonna add those files. You need to go to the proper folder, of course, and then to the place where I actually have them. I need to copy all of them, of course, except for these two, right? Now here is an interesting thing. Well, by default in this version 2019.1, it will copy these files onto a particular folder. I think I already mentioned that, by the way. It will create here a folder called SRC, and it will place those files there. You can do that, or you can just uncheck it, and they will be kept under the HDL. Okay, Either way is fine, okay? It doesn't really matter how you do it, as long as you add them. Okay? In this case, I didn't select that, even though the tutorial says you can, but I didn't select that, and a source file was not created. But in the right here, now we have it, right? And of course, they are in the file VHDL. Okay, so this is the COM2IP, right? This block, remember, is this block here in red, and all it does is actually implementing what? Here is the register and the state machine, and I guess a counter too is required there for some reason, and then some glue logic to interconnect the register signals to the input. Okay, and that's all that we have there. Okay, and of course this block here, this is my circuit, right? You design that however you like, however you prefer. Okay. So notice one important thing to tell you is that whatever you design, make sure that it receives inputs, and there is a qualifier for the input, and then once the data output is processed and computed and ready to be out, you qualify the output with a V signal. Okay, if you forget to do that, there is no way for the AXI4-Lite interface to know that you have correct data. So you have to do it. Okay, has to be that way, or at least resemble it in some ways. Okay, so then what now? Again, I am just repeating the steps as laid out in this tutorial. Okay. Again, there is no need to add any ports, right? Because we don't have external ports. Like I said, if you want to add new ports, you will have to add them into this file, and then into this file as well, right? All the way up to the highest. Let me see. All the way up there. Okay. You will see. Some of you might need to do that. Maybe your circuit, you want to include like a LED, right? For some reason, right? Or as hopefully we will see later, I would like to create an interrupt from my hardware into the software system. You need to create the interrupt signal there, for example. Okay. Okay. So now what do? Just to double check, of course, we run synthesis to see if something might be incorrect, right? Something is amiss. Okay. And this is the, and this step, once you complete this step, believe me, everything is going to be very, mechanical, very straightforward, right? It might take some time, of course, because Vivado takes a while to synthesize, implement, and generate the bitstream back. But as you can see, the most important part is what I am doing right now. Okay. So again, here, let me repeat myself. What did we do? I already had this thing ready. I already had a project for the interface already ready. I had this entire thing ready already with the test bench to double check, that everything is working fine. And all I need to do now is to build the peripheral in Vivado. Okay. Okay, let's take a look. Usually it takes a while, especially with my recording. It even takes longer. So let's give it a little bit of time. So now it completed. Of course, we do not run implementation. We stop right there. And now we're ready. Remember, what do we have to do in this particular piece of software? Well, we have to merge the changes in the file groups because we added new files, right? So we merge the changes. It's like we have to tell Vivado that we actually did that. And then we just, we say we package our IP. Okay, this step, by the way, is very important because this is a step where the IP is going to be placed into the library of Vivado, so you can just, next time you can drag it and drop it onto any new project that you like, by the way. Okay. Yes. And now, believe me, now everything will be very mechanical. So what do we do? Remember, we in this new project, right? We open the canvas, and then what we need to do is to sorry, where is it here? To just drag and drop the components. Okay. It's taking longer than I expected. Let's give it a little bit of time. Here we go. So what I'm gonna do, add IP, look for the PS, of course. And then look for the MyComp. Somebody might say, well, what about the pixel processor that we developed last time? Unfortunately, it doesn't show automatically. In the tutorial, it will tell you how to make sure to add, a particular previously generated IP into your project. Okay, it's just clicking into the project repository. That's all that you need to do, by the way. Okay. So let's do that. Let's use this one here. And then, this is just click and click. It's even simpler than the second tutorial, by the way. Because in the second tutorial, we needed to include extra IOs, right? Here we don't, because your peripheral is only communicating with the AXI-PS. We reorder the blocks, and then we validate, just in case something might be wrong. We go to sources. Once everything is ready, what do? We create the HDL wrapper. Okay. Again, this example, luckily for you, in this example we do not need text files, right? So we don't need to do this weird thing that we did manually for the pixel processor. Okay, this is much simpler. Okay, here it is. The wrapper is ready, I think, and that is the top file of your design. Okay. Let's give it a little bit of time. Now we're ready, and now I think I'm confident enough. I'm gonna go all the way to generate bitstreams. Okay, while this is running, let me explain to you about the following. Like I said, the second step is the add or create the interface circuitry for this flow. Say you have a circuit, like the circuit, for example, for your final project, right? Your first job is to create your circuit, right? And test it out, right? I mean, with simulation, of course. I mean, simulate it comprehensively. And then the second step is to add the interface circuitry for AXI4-Lite, right? And simulate it. Now simulation is going to be a bit harder here, because if you remember, this file here, right, had a lot of signals, right? And let me just show you again, just in case. Right, look at that, look at all those signals, right? And you now have to create a test bench for those. Okay, how do you even start doing that? Well, you will have to read carefully, right, into the notes, right, to figure out how those signals actually work. But if you want to, of course, have a shortcut, I have already created a test bench, right, for, let's say, for the COM2, but it can be used for your circuit anyway. Okay, I have already created this test bench where I implemented, the entire protocol. Right? We first send the right address, then we send the data, right, and then we we send the we wait until remember all of these 4 signals are 1, right? And then we write the right response channel, right, with the acknowledgement. So this whole thing is actually how you send one particular word over the AXI4-Lite. This is how you write on a particular register. Okay, but you see it's more complex, right? You need to send the right address, then you need to send the data, then you need to implement the response, assuming you get the actual response. Okay, so all of that is implemented for that to you here. And for those of you who are curious about VHDL, well, since we have to do this all the time for every single word, right, I will have to copy and paste this all the time, right? So I do not want to do that, of course. And what I did instead, I actually packaged all of that into what I call a procedure in VHDL. It's called procedure write register. And then there is another procedure that is similar, which is called read register. And it includes the following. You send the read address, and then you read the data. Okay? So there are a lot of moving pieces here, by the way. So now, when you have the test bench, what do? Well, of course, you always warm up the UUT, right? The clock and the stimulus. What do? Oh well, look at this. How are we supposed to test the this comp? Well, you need to send actually 3 of these words, whereas in the last word only 8 bits will be used. You send 3, 1, 2, and 3, and then after a while you retrieve 20 bits only. So let's implement that, right, in the test bench. So we do it by using what? This write register. So the first time we use what? We send this. To which register? Remember, register 0, right? Because that's what we want, right? Register 0, if you remember. The second word will be sent to register 1, then to register 2. The second word is here, and that is register 1. The third word, from which we only use 8 bits, will be on register 2. Okay? The procedure already takes care of identifying all of these constants for you. Okay? You don't have to do it again. And then, of course, you do a loop, of course, and you have to wait for what? What is it? What is this? You remember? O data should be, if I am not mistaken, the following. We read a register, in this case the register 3, right? Right. And the bit number 20, which is the V, because I happen to put that V on 20, although I could have put it anyway in the 32-bit, but I prefer to put it as the MSB. So I have to check this. So this thing is being read already, by the way, by this register. I have 32 bits already ready. That's what I am actually reading, by the way, in my test bench, the 32 bits. Okay, but it happens to be that the bit number 20 of these 32 bits is actually V. So I have to check that this V is actually 1 to know that the data here is actually valid. So that's why I have here a small loop in hardware. Let me see. Sorry, in software. What is it? Yeah. I have a small loop here that it exits this loop whenever the bit is 1. Whenever the bit that is read here is 1. Okay, and when that happens, you will have your data ready on where? On this signal, right? On our data for you to read on the simulation. Okay, and the answer should be this. How do I know it's this? Because I have tested already. What is it? I have already tested this block, only this block on its own, right? And that's the data that I got. Now, of course, if I test the whole thing and I feed the same data, sort of, I am supposed to get the same data out. And this is what I should get. Okay, there you go. And here I try a second example, right? 3 different values, and then I get other values here. Okay. Now, of course, make sure that this value stays, right? So that's why here I actually set it to 0 first before I attempt to read again. Okay, and this is the answer. Okay, so if you are working on a project like this, I would recommend you use this technique, right, to write onto registers and to read from registers, and then on your simulation waveform you are supposed to see the proper data. Okay, if you're curious about that, I think I have no, not here, sorry, just a moment. If you are curious about that, I think I have a timing diagram, right, in the notes. This timing diagram is actually for the pipeline divider, but it works the same way, right? Here is the data, and here are all the signals. Okay. By the way, the pipeline divider is also available for you to download and use. In fact, if you go to the tutorial, right? I think the second example, because this one we're doing right now is the third. The second example, let's see, that's the pipeline divider. Okay, so, and of course this circuit here, the whole thing already includes a test match as well, which actually implements this waveform already. Okay, if you want to see. Okay, so let's keep going then. So what we're gonna do now, assuming everything is working fine, you never know, but we wait until we get the bitstream. As you can see, it takes a while. It takes even longer when I am recording. So let's give it a little bit of time, okay? Okay, now it finally completed. So, but you know now what you have to do, right? All you have to do is to go to here and export the hardware to the SDK software, and then open the SDK software. Okay. And according to the tutorial, what we're gonna do is to just run this file, right? Which I have it ready for you, of course, because that is in the list of files, right, that you can download from the tutorial. That's this .c file, which again, feel free to use when you are creating your own interfaces. You can use that as a template, of course. Okay, let's give it a little bit until the SDK completes launching. Okay, and now now that this is open, we're gonna go and create a new project, right? A new software application project. I'm gonna call it com to test, and it will be an empty application. Okay. Now what I have to do, of course, is to remember manually. I think you might discover even better ways to do it, but this is the way that I'm stuck with. I just developed this. Okay, we're gonna copy that onto the folder, right? Which should be, I think, right here, SDK and comp test source. You have to, of course, wait until it completes creating the folders, and then you paste your .c file. And now you're here, and for some reason you have to now refresh it, right? F5. So you will refresh, which means it will add the file to the SDK, and it will also build everything automatically, because by default, the build automatically feature is on. For some reason in this, I don't know, I hope it doesn't happen to you, but in this Windows 10 computer, this process takes a long time. I have another Windows 8 laptop, where this process actually takes almost nothing. It's almost automatic or instantaneous. Here, for some reason, this can take a long time to build. Okay, so let's wait until that process finishes. Okay, while we wait for this to complete, just let me explore here the driver, right? Every time you create an IP, Vivado will add automatically the driver. The drivers are just simple, I hope this opens, yeah, simple examples that has a bunch of functions, only two here, which is my comp2 right on the slave register. That's the function that you have. So you indicate the base address of your peripheral. By the way, Vivado will provide an address to your peripheral. I think by default, the first one is always 43C00000, and it's usually in the range of 64K bytes, by the way. Okay, so that's the address. So we need that, of course. And then you need the register offset, 0 for register 0, 4 for register 1, 8 for register 2, and so on. And the data that you want to write. Okay, again, this is just a function that is essentially this function here, this particular block. Because look at this block here. This block is already, that's the most basic function actually, which you can use no matter what. It includes already the base address, but now of course you have to add here the offset and then provide the data. So, and then that's for writing, right? And another one is for reading. The same, right? You read the base address, that's an offset, of course. Remember, this is just this simple XIL function, which is I think one of the most basic functions in the kernel. Okay, to read and write. Okay, so if you want, you can just forget about this, right, and just use this XIL in and XIL out for everything. Okay. You can do that as well. Let me see if this thing has completed. Not yet. Just gotta give it a little bit more of time. Okay, so now that it's completed, now we can actually run the software. So this is the piece of hardware software that I have. It's just a bunch of instructions here. We write these three words on the particular register. Notice that I'm using this particular function as opposed to the other. I could have used either one. Okay, and then I read from register number 3. Okay, I run it for the first case and then for the second case as well. Those two cases are explained right here, as you can see. Okay, and this is the expected result. Okay, and also for the ones that you're curious, I'm also testing a time measurement thing. Okay, if you're curious, you can look at it. I am measuring the time it takes to compute this. Okay, so let me open my let me turn in my turn on my ZYBO Z7, and now I am going to program the FPGA. Just give it a little bit, and then I go to my SDK terminal. I'm going to open a connection here in this content, and now I am ready to run the software, right? Remember how you do it? Run as, and this will run. Okay, let's just give it a little bit of time, and there you go. So for example, for the first set, right, the data is right here. The result is 00102B82, which is what I expected here, and the second one is 1018FF, which is what I expected here. And I measured the time for the first case, and it takes about 1.5 microseconds. Okay, these things are, I think, different just testing numbers. What matters is this elapsed time. Okay, and that's how I finish this experiment. Okay, thank you so much. Thank you.